Okay, so we will talk about divide and dynamic programming. So, it is a design technique like divide and conquer. Design technique similar to divide and conquer, but we will see by taking one problem, one example, which is called longest common subsequence problem. Longest common subsequence, which is also called LCS problem. So, in this problem we have given two sequence x and y, say x is of length m and y is of say length n, and we have to find the longest common subsequence. For example, suppose x is say x is a b c b d a b and y is say b d c a b a. Suppose these two are the given sequence x and y, and we have to find out the longest common subsequence between them. So, how we can get a longest common subsequence? So, then so b c a b, this is a common subsequence of length 4. So, any we can verify we cannot get any subsequence of length 5. So, length 4 is the longest length of the longest common subsequence. So, can we have any other longest any other subsequence of length 4? So, we can take b so we can take b d a b. So, there could be many. So, it is not unique, but we want to get, the problem is to get a longest common subsequence, that is our problem of LCS. Okay. So, what is the approach, what is the naive approach we can think? So, we can choose a subsequence from this sequence and we can check whether this is a we can choose a subsequence from this, we can check whether this is a this sequence is a subsequence of this or not. So, for that if we take a sequence from subsequence from here to check whether this is a subsequence of this, it will take order of n, because length we have to just scan in the worst case, and there are how many subsequence we can have. So, this is basically power set. So, 2 to the power n m. So, it is basically n into 2 to the power m into n. So, this is the exponential. So, this approach is not good because it is not polynomial time. So, we want to see whether we can get a better algorithm to finding the longest common subsequence. So, for that we simplify this problem in a way that, so we look at the length of the longest common subsequence. Simplification. We look at the length of the longest common subsequence, and that length is unique. In our example, it was 4. So, we want to find first we have a simpler version of this problem. Instead of finding the longest common subsequence first, we first find the what is the length of the longest common subsequence, and then after getting the length we will try to get the a longest common subsequence. Okay. So, we denote this length by we denote a notation L of yeah, we just denote it by Cij. Cij is basically length of the longest common subsequence of the sequence up to I. This is the prefix, this is the y prefix. Okay. So, we have a x sequence and we have a y sequence. So, this is from 1 to m and y is, this is x, this is y, and y is from 1 to n. Now, if we take I over here, we take a prefix of this, we take a sequence up to I and we take a sequence up to j for y, and we consider the longest common subsequence between these two, and this length of the longest common subsequence is denoted by Cij, C prefix ij. Okay. Now, if we can find out Cij for all ij, then we are done. Why? Because we are looking for the length of the longest common subsequence for full sequence x and y. So, basically Cmn will give us that. This is the length of the longest common subsequence for the x and y, Cmn. So, if we can get all the Cij's, so from there we can just get the Cmn, and that will give us the longest common subsequence, length of the longest common subsequence. Okay. So, now we will use a theorem for to have a recursive formula to find the length of the longest common subsequence. Okay. So, that recursive formula is telling, this is a theorem. So, Cij is of the form C I minus 1 comma j minus 1 plus 1 if xi equal to yj. Otherwise, if xi not equal to yj, then it is maximum of, excuse me, C I I minus 1 comma j comma C of I comma j minus 1. This is if xi is not equal to yj, otherwise. Okay. So, this is the recursive call for finding the longest common subsequence, length of the longest common subsequence. So, we need to prove this. So, we will just try to see the first part and then the second part will be the similar. So, to prove first part, we assume this case where xi is equal to yj. So, this is our x sequence and this is our y sequence, and this is I, this is j. Now, these two values are same. Okay. Now, let I can erase this. Okay. So, let z be the longest common subsequence of x 1 to I comma y 1 to j. Okay. Now, and we are assuming the length of the longest common subsequence is k. So, basically this is so now we claim that this last one has to be the common value of x and this. Why? Because otherwise, if this is if x z of k is the letter below this, then we can add these two and we can have a one more length k plus 1, which contradict that the length of the longest common subsequence is k. So, the last alphabet of this longest common subsequence has to be this common value. Okay. Now, if we take z minus 1, then this is a common subsequence of x 1 to I minus 1 comma y to j minus 1. Okay. Now, we have to see whether this is a longest common subsequence of this or not. So, that is our claim. Our claim is this z is a longest common subsequence of okay. So, this will prove by using the contradiction method, cut and paste technique. Suppose it is not, suppose this is not a longest common subsequence of these two. So, we have a longest common subsequence whose length is more than this. So, suppose that is W. W is a longest common subsequence of whose length must be more than this. So, it must be at least k. Okay. Now, we can just take W and this is cut and paste technique. So, this and this value is same as y of j. So, this will be a longest common subsequence for this x 1 to I and y 1 to j, but length of this is k plus 1, which contradict the fact that the length of the longest common subsequence of this is k. So, this claim is true. So, this is the longest common subsequence of this. So, that means this is the length of the longest common subsequence. This is k, which is basically k minus 1 plus 1. So, this is basically this, just now we have seen this is the length of the longest common subsequence, this plus 1. So, this is the first part of the proof of the theorem, and the second part also similar, where if they are not equal, if these two values are not equal, then we take the maximum of this one indices is less. Okay. So, that is the recursive formula. Now, we use this formula to have a algorithm for finding the length of the longest common subsequence of x and x prefix up to I and y prefix up to j. So, this is the recursive algorithm. For LCS. Okay, so we are going to find the LCS of. So, if xi equal to yj, then Cij is equal to LCS of x comma y, then I minus 1 j minus 1 plus 1, else Cij is max of LCS of, I mean length of the longest common subsequence actually, this or I j minus 1 indices is less. Okay. So, this is the recursive call for finding the length of the longest common subsequence of x and y. Now, when is the worst case? Worst case is when xi is not equal to yj, and in that case we have to take two calls with each indices 1 less, that is the worst case. Okay. So, now we want to see the worst case recurrence for this. Okay, so the recursion tree for the worst case, we take m is equal to say 3, n is equal to 4. So, we want to find out the longest. So, this is the worst case. So, for this we have to calculate, this is one less. So, 2 4 and 3 3 and here 1 4 then 2 3. So, here 2 3 3 2 like this dot dot, then here 1 3, then here 2 2 1 3 2 2 like this. So, if you see this part is same as this part. So, this is the extra work we are doing, this is the overlapping, this is the repetition of the sub problems. So, when you recursively call it, if you do not store the value, then we have to unnecessarily we have to do the many computation. This is the repeated calculation we are doing. So, this is one of the hallmark for dynamic programming problem. If we see in our problem we have such kind of repetition, our mind will be think that okay, so this is a indication that we should go for a dynamic programming problem. This is one hallmark for dynamic programming problem. So, let us write the hallmark. So, hallmark 1 is basically, this is hallmark 2. Hallmark 1 is basically telling optimal substructure. This hallmark for dynamic programming problem. So, when we will think that okay, maybe we have to go for a dynamic programming technique. So, this two is the indication. So, first indication is optimal substructure. So, this is telling us an optimal solution or solution instant to a problem content optimal solution to the sub problems. Okay. So, this is the first hallmark for dynamic programming problem. So, an optimal solution of a problem. So, this is telling us if we have a z LCS of x and y for the full sequence. Now, if you take any subset of any prefix of z, now that we have already seen that will give us a LCS, longest common subsequence of the prefix of corresponding x and y. So, that is the optimal substructure. So, if we have the solution of the whole problem, then that will contain the solution of the sub problems. Okay. And this is the basically hallmark 2. So, it is telling us overlapping sub problems Okay, so it is telling us a recursive solution content A small number of distinct subproblems repeated many times. Repeated many times. Okay. So, this is the overlapping sub problems problem. For example, here we are repeating this calculation. So, that is one indication that we should think now we have to go for the dynamic programming problem. So, to avoid that, what we do, we will memorize the value. Once we calculated this C23, so we will store it somewhere, so that for this branch we do not need to calculate again. So, this is called memorization or memorization. So, we will memorize this value in order to avoid the repetition in the calculation. So, let us have that modified version of that code, this recursive code. So, this is the memorization algorithm. This is the recursive algorithm. So, once we compute some value, we will store it. We will to avoid the same computation in the future. So, that is why. So, the code is similar to earlier, only thing. So, we will only do the calculation if the Cij is nil. Otherwise, if Cij is already calculated, we will not do it again. So, that check we have to do if Cij is nil or it is have some value. Then we do the same thing. Do if, then the remaining part of the code is same. Then Cij, that is the recurrence, is basically LCS of x comma x y I minus 1 j minus 1 plus 1 else Cij is basically maximum of this part is same. This is the coming from the that recurrence, one index is less comma LCS of. Okay. So, this is the way we avoid the repeated computation. So, this will handle using the in a table. We compute this in a bottom up way. So, this is the dynamic programming problem for this dynamic programming approach for solving this problem. So, the idea is to compute the table bottom up way. So, we will compute the table bottom up way, so that we will avoid the computation. So, let us take the same sequence. So, our sequence was, so let us have this table. So, the sequence was A, B, C, B, D, A, B. This is the x and y is B, D, C, A, B, A, B, D, C, A, B, A. So, okay. So, we will just okay. So, this is the x sequence, this is the y sequence. Now, we initialize, so this initialize by all 0. Now, this is 0 because this is this sequence with null. So, this there is no common subs length. This is basically Cij's table, and we will use that formula to find this value. Now, we check this and this. So, these two are different. So, this will be 0 according to the second formula, maximum of these two. So, now we come here. So, this sequence, so these two are same. So, what we do? we take this plus 1. Similarly, these two, maximum of these two 1, 1. So, this is basically common. So, this is like this, and we have 1, 1, 1. So, similarly, if we do this here, so this is 0, this is not common, maximum of these two, this is maximum of these two, 1, this is also 1, and now we have a common over here. So, this will come 2. So, 2, 2. So, let me just finish this. So, we are using that recursive formula every time. So, see, so this is basically 0, then this is basically 1, maximum of these two, then this will become 2, then this is 2, and this will become 2, 2, 2, and then we have a 1, 1, 2, 2, 2. Now, we have a common over here. So, it will be 3, and then maximum of these two is 3, like this. So, 0, no, this will be 1, because maximum of these two, this will be 1, and then we have a common, this will be 2, 2, then again we have a common, this plus 1, 3, we are using the formula 3, then 3 again, then 3, and this will be now 4. Okay. And this is 0, this is again 1, 2, 2, 3, 3, and this is common, this plus 1, 4, and this is maximum 4. Okay. So, this is the table for Cij's. Now, so this is the Cij is basically, Cmn is basically 4. Okay. So, this way we are getting the Cij, this is the dynamic programming method. So, this is, we are not calculating, we are not repeating the calculation which we have already did. So, now from here how we can get the, this is the length of the longest common subsequence, how we can get the longest common subsequence? We will follow this path, we will follow this link, and we will get the longest common subsequence. So, this is because of A. So, A, and then if we take this, this is B, and then if we take this, this is C, and if we take this, this is B. So, this is a longest common subsequence. Okay. So, we first find the length, and from there we get the longest common subsequence. So, what is the time complexity for this? It is basically to compute this table, it is basically order of m into n. Okay. So, this is the technique of dynamic programming technique, and we will use this technique in the graph algorithm. Thank you.